Welcome to the deep dive. We take your sources, the articles, the research, all those dense white papers, and we deliver the essential insights.
And today, we're tackling one of the big ones.
We really are. We're decoding the quantum world. Our mission is to, bridge that gap between really abstract physics and the actual cutting-edge engineering that is remaking our technology.
Everything from materials science all the way to computation.
And to do that, we're starting not in a lab, but, well, right here in the macro world.
Right at the boundary between that microscopic quantum realm and our everyday reality.
That's a great place to start because our sources highlight something truly remarkable.
The 2025 Nobel Prize in Physics.
Exactly. Awarded for research confirming that nanotechnologies, that whole world of the extremely small, can absolutely be observed at the macroscopic scale.
We're talking 10 by 10 micrometers, which sounds tiny, but in that world, it's huge. It's a watershed moment.
How so?
Well, for decades, we've treated quantum mechanics as this thing that's, locked away, relevant only for a single atom or a subatomic particle.
Right.
This confirmation forces us to rethink things. It's a philosophical reassessment.
So if quantum effects can suddenly pop up at this scale, could certain phenomena that science still struggles with?
Things that seem almost supernatural?
Yeah, exactly. Could they be connected to quantum mechanics?
That's the core question. And our source material points to specific things like ball lightning.
Ball lightning.
Highly energetic phenomena. They defy classical explanation, but they show three distinct traits that feel very, very quantum.
Okay, let's break those three markers down. What's the first one?
First is probability, or non-determinism.
Meaning?
The phenomenon might occur under a certain set of conditions, but it's not a guarantee. You can't just flip a switch and make ball lightning appear.
So it's not predictable like, dropping a ball and knowing it will fall.
Precisely. The second trait is observer dependence.
Ah, the Schrodinger's cat idea.
Exactly. The outcome, or even if the thing keeps existing, seems to depend on an interaction with an observer.
Which is why so many of these stories are anecdotal, right? They're impossible to document.
Because the moment you try to fully measure it, the state collapses. The quantum signature disappears.
Okay, and the final trait?
High energy density. These things require a huge concentration of energy in a tiny volume. Ball lightning fits that perfectly, so you see that combination.
High energy, non-determinism, observer dependence.
And you might be looking at quantum effects bleeding into our world.
And that transition from philosophy to actual tech is where it gets really interesting. Let's dive into the quantum technologies that are already here, starting with precision.
The revolution in precision is, it's already happening. It's driven by quantum logic clocks.
Like the ones at the NIST laboratory.
Yes, based on aluminum ions. It is, right now, the most precise clock on the planet.
And the number is it's staggering. It's expected to be off by no more than 1 second in 3.7 billion years.
I know, it's precision on a cosmic scale.
So why do we need a clock that's that good? What's the practical application?
Navigation and synchronization. Current GPS is great, but its accuracy is still measured in meters.
Okay.
If we can shrink these quantum clocks down and use them for navigation, we improve that accuracy from meters down to centimeters.
Meters to centimeters. That's a huge jump for things like self-driving cars.
Or infrastructure monitoring, exactly. It's transformative.
Yeah.
And then there's secure communication.
Right. Quantum communication.
Mm-hmm.
This is where you transmit information encoded in quantum states.
Using entanglement and superposition, yes. And that's where you get quantum cryptography.
How is that so much more secure than what we have now? Our current encryption is just based on really hard math problems, essentially.
Well, classical encryption is based on computational difficulty. It would take a supercomputer a very, very long time to break it.
But not impossible.
Not impossible.
No.
Quantum cryptography offers absolute secrecy because the encryption is based on the laws of nature.
What does that mean in practice?
If someone tries to intercept or even just measure the quantum state that's carrying the information, that very act of measuring it causes the state to collapse.
Ah, so you know immediately.
Instantly, the legitimate users are alerted that it's been compromised. Passive eavesdropping is physically impossible.
That's a security guarantee rooted in physics. That's unbeatable. And we're also seeing quantum teleportation, at least over short distances.
Correct. And we need to be clear, this isn't Star Trek. We're not beaming people around.
Chuckles, right.
We're talking about the instantaneous transmission of a quantum state. We've seen electron states teleported over 100 kilometers in Europe. A U.S. team did 44 kilometers back in late 2020.
So this is the groundwork for a future quantum internet.
That's the dream, information that travels instantly and with perfect security.
Okay, so beyond communication, these ideas are reshaping physical things. Let's run through some real-world impacts.
Yes. The biggest one might be energy. A huge amount of energy is lost just in transmission.
In power lines.
In power lines, yeah. If we can solve high-temperature superconductivity, which is a quantum mechanical problem, we could create lossless power lines. We'd save maybe 10 to 20% of all energy generated.
Wow. And nanomaterials are also changing manufacturing.
Absolutely. The details on composites are fascinating. You take a polymer compound and you add just 5% organoclay by mass.
Just 5%.
Just a tiny bit. And the material's properties just fundamentally change. They become dramatically stronger, more durable.
And these are already in use.
Oh, yeah. In automotive parts, in high barrier packaging films. And looking ahead, we have nanoglass for transparent screens, maybe even concepts for invisibility.
By manipulating light at the nanoscale.
Exactly.
Okay, let's pivot to the thing that's driving all this computation. Why can't our classical supercomputers handle quantum problems? Why do we have to build these entirely new machines?
The issue is it's the exponential growth of complexity.
Right.
Classical supercomputers are great for classical systems, but when you try to model a quantum system, a complex molecule, a new material,
You're saying the problem just gets too big too fast.
it explodes. For example, if you're modeling electron spin, adding just one more electron to your model doubles the computational power you need.
Doubles it.
Every single time. The current record for modeling these interacting spins is only around 40, but a new drug or a battery material might need thousands. Classical computers just can't do it.
So we have to move beyond the classical bit. Let's really define the difference between a bit and a qubit.
So a bit is your basic unit of classical information. Physically, it's a macroscopic thing, maybe thousands of atoms in a magnetic domain.
And it's either a 0 or a 1.
A single discrete value, 0 or 1. Simple Boolean logic. A qubit, or quantum bit, is the quantum version. It might be a single charged atom or an ion.
And its power comes from two principles. The first one is superposition.
Superposition is the magic, really. It means the qubit isn't stuck at 0 or 1. It can be in a combination of both states at the same time.
So it's probabilistic.
It's a probability wave. It could be, say, 30% state 0 and 70% state 1.
Which brings us to our favorite analogy for this.
Slight laugh. The pizza joke.
The pizza joke.
While the pizza's on its way to you, it's in a superposition of all possible pizzas you could have ordered. It's 4 cheese and pepperoni and mushroom all at once.
Until you open the box.
The moment you open the box, that wave function collapses into the single classical pizza you actually got.
It's a perfect way to think about it.
Yeah.
So how do you visualize something that's both 30% and 70% of two things at once?
That's where the block sphere comes in. Imagine a globe. A classical bit can only be the North Pole, that's 0, or the South Pole, that's 1.
Just 2 points.
Right. But a qubit state is a vector pointing to any spot on the entire surface of that sphere. It shows you the infinite combinations it can hold before you measure it.
So that's superposition. The second source of power is entanglement.
Entanglement is about connection. It's a single quantum system made of 2 or more particles. Once they're linked, they stay instantly connected no matter how far apart they are.
Even light years.
Even light years. If you measure one, you instantly know the state of its partner. They're not separate things anymore. They're a single unified system.
And putting superposition and entanglement together is what gives you this massive computational leap. What's the scale of that?
It's exponential. A classical computer with n bits can only track n values. A quantum computer with n qubits can simultaneously represent 2 to the power of n values.
So let's put a number on that.
A system with just 300 qubits has 2 to the 300 possible states. That number is, and this is not an exaggeration, larger than the estimated number of particles in the observable universe.
That is just hard to comprehend.
Yeah.
Which brings us to the race for quantum advantage. What are we physically using to build these qubits, and what's the biggest hurdle?
Well, we're using a few different things. Superconducting circuits, ion traps, even light-based photonic systems. But the biggest challenge for all of them is something called decoherence.
It sounds like the quantum version of your computer crashing.
That's a good way to put it. To keep that delicate superposition state, the system has to be completely isolated and cooled to near absolute 0.
So any interference.
Any interference, a stray magnetic field, a tiny vibration, a change in temperature, and the wave function just collapses. It snaps back into a classical 0 or 1, and your calculation is destroyed.
How long do you have before that happens?
Right now, we're talking hundredths of a second. You're always fighting the environment.
And this struggle defines quantum advantage. What is that exactly?
Quantum advantage is that moment when a quantum machine does something that is practically impossible for the best classical supercomputer. The threshold is generally thought to be around 50 qubits.
Which is 2 to the 50 states.
Right. And we've seen some big claims here.
Yeah, Google's Sycamore processor.
Sycamore, at 54 qubits, claimed it solved a specific problem in 200 seconds that would take a classical supercomputer 10,000 years.
Though that was disputed.
It was. IBM argued they could do it in about 2.5 days. But even then, the gap is huge. And China's Juzhang photonic computer did a calculation that would have taken a classical machine 1.5 billion years.
So the potential is clearly there. What's the roadmap look like for getting to a truly functional machine?
The big players, like IBM, are promising machines with 4,000 physical qubits by 2025.
Okay, that sounds like a lot.
It is, but here's the catch. Because of decoherence, most of those physical qubits are just used for error correction. To solve real-world problems, we'll need closer to 1 million logical qubits.
Logical qubits, meaning stable, error-corrected ones.
Exactly. So these aren't going to replace your laptop. They're specialized tools.
So how do the algorithms actually work? If it's not just brute force, what is a quantum algorithm doing?
The core mechanism is interference. You're basically engineering the probability.
How so?
The algorithm manipulates the wave functions so that the paths leading to the wrong answers interfere destructively.
They cancel each other out.
They cancel each other out. And the paths leading to the correct answer interfere constructively, which amplifies its probability. So the machine doesn't give you one answer. It gives you a probability distribution that hopefully peaks right at the correct solution.
It's an entirely different way of thinking about computation. Which brings us to computational chemistry, using quantum mechanics to predict the properties of materials without ever running a physical experiment.
This is the whole idea behind the first principles or ab initio approach.
Instead of the old way.
The old way was painstaking. You test a material, you add something to it, you run new tests, you build up these huge databases of what happened.
And the ab initio approach.
It's predictive. All you need to know is the elemental composition, what atoms are there and where they are, and you can calculate the structure, the energy, the reactivity of the final material.
And this all comes down to solving the Schrödinger equation. Why is that so hard?
The Schrödinger equation is basically the quantum version of Newton's second law. It describes everything about the electrons and nuclei. But for any system with more than a couple of atoms, it's just mathematically impossible to solve directly.
It's a many-body problem.
It explodes exponentially, so you have to rely on approximations. And the breakthrough that really revolutionized the field was density functional theory, DFT.
Why was DFT such a game changer?
Well, instead of trying to solve that impossibly complex wave function, which depends on the coordinates of every single electron,
Which is a huge amount of data.
a ridiculous amount, DFT realized you could reframe the problem. You focus on the much simpler electron density.
And electron density only depends on 3 coordinates, no matter how many electrons you have.
Exactly. So DFT basically skips the hardest part of the equation by solving for an equivalent, simpler quantity. It was a massive simplification.
Which means you can get results that are close to experimental data, but with much less computational cost.
Right, though it still struggles with some subtle things like van der Waals forces. But the ultimate constraint is always this trade-off between system size and accuracy.
What do you mean?
If you need the highest possible accuracy, you're limited to modeling maybe 100 atoms. If you want to model a bigger system, say 1,000 atoms, you use DFT, and the accuracy is a bit lower.
And if you need to model 100,000 atoms,
Then you have to use methods like molecular dynamics, and you sacrifice a lot of quantum accuracy to get to that physical scale. You have to pick your poison, precision, or size.
okay, let's ground all this in one final concrete application. Let's talk about welding.
It sounds mundane, but it's a huge challenge. Welding highly alloyed steels, the kind used in pipelines, offshore platforms, ships, it's very difficult.
The welds are weak points.
They can be, but the nanotechnology solution is to intervene right at the moment the metal solidifies.
How?
Researchers introduce specific nanoparticles, like titanium nitride or silicon carbide, right into the molten weld pool. A tiny addition.
And this changes everything.
It changes the physics of the system. Those nanoadditives fundamentally alter the crystallization front. They act as seeds for new crystals to form.
And by changing the crystal structure, the microstructure.
You change the final mechanical properties, the strength, the durability, the corrosion resistance of the weld joint.
So researchers are using calculations like DFT to predict which nanoparticles will work best before they even do the experiment.
That's the synergy. They use calculations to model the nano interactions, and then they use physical simulation machines to test the results. It's this combination of computation and experiment that's designing the next generation of materials.
This deep dive has really spanned the full spectrum, from, philosophical hints of quantum effects in nature to the reality of quantum clocks,
To the mind-bending scale of 2 to the 300 states.
and all the way to using this theory to predict the materials of tomorrow.
We really are living through a second quantum revolution. It's defined by our ability to actively manipulate these individual particles for real, tangible outcomes.
So if we step back for one final provocative thought, something our source material raises, given the sheer complexity, the non-deterministic nature of it all, what does this suggest about the world around us?
The ultimate implication is this. If a system requires a quantum computer to truly model it, well, maybe our entire universe can be seen as a single giant quantum computer.
Or a simulator.
A simulator that is constantly computing itself into existence. Which means we aren't just observing reality, we might be the calculated result.